In this lecture we've been looking at the phases of matter. So we've been considering solids, liquids and gases and thinking very carefully about what happens when we move between the states of matter. Most of the work that we've discussed here I would put down as revision for you. Maybe not the stuff about phase diagrams, which we'll cover at the end, but certainly the stuff where we're talking about the specific heat capacity and to some extent where we're talking about latent heats as well. So going back to the beginning of the lecture, the first thing we looked at was the amount of energy that we need to provide to atoms and molecules that are in one state to heat them up. And we saw that this depends on the mass and the specific heat capacity. Okay, so the amount of energy we need to supply is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature. Okay, so from there we've gone on and looked at latent heats. And latent heats, if you remember, are the energy that we need to change state. So where does latent heat come from? Well, if you remember the last lecture where we looked at atomic potentials, we saw that to separate two atoms we needed to supply a certain amount of energy, and this in some ways related to the latent heat. What we find with latent heat is that the latent heat of fusion, that is the latent heat required to move from solid to liquid, tends to be much less than the latent heat of vaporization, because when we vaporize something we need to move the atoms and molecules a long distance apart. So we've looked at those things and we've seen that as we heat up an object, the heat increases till we reach a change of state. When we reach the change of state, the temperature remains constant while the latent heat is supplied. Then when all of the material has changed state, we find that the temperature again increases till we reach another phase change. Okay, so from there we've gone on and looked at phase diagrams, and we've seen that pressure is important as well as we change state. So we saw, for example, in the demonstration that we could take water and we could boil water at room temperature just by reducing the pressure. From this we get so-called phase diagrams, where we can see in a phase diagram what happens is that we have one axis, the y-axis, which is pressure, the x-axis, which is temperature, and we can see curves occurring. So we get a melting point curve, we get a sublimation curve, and we get a vapor pressure curve as well. On each of those curves we find that that material can exist in two states, and we find a particularly special point called the triple point, where solid, liquid and vapor can exist in equilibrium with one another. If you have a look, we've provided the curves for water, and we've looked at the curve for CO2, and we've seen that CO2 at atmospheric pressure in fact sublimes, so it moves straight from a solid into a vapour. If we want liquid CO2 we have to increase the pressure, and that's exactly what we find with fire extinguishers. Okay, in a fire extinguisher we have liquid CO2, so we keep it liquid at room temperature by increasing the pressure, and that when we want to blow the fire out using large volumes of CO2 gas, we get that as we release the pressure, so the CO2 turns into a gas. Finally, we looked at some more exotic phases of matter. We looked at Bose-Einstein condensates, and we also looked briefly at plasmas. As I say, there are more states of matter. This is a subject which can advance much further. We've just seen a brief introduction today. Next lecture we're going to go on and start looking at electrons and what makes up the atom itself.